Xinfei Wu, Department of Academia Industrial Collaboration of the Science Park Affairs, the winning teams, distinguished guests from foreign offices, State of New Mexico Taipei Office Director Ethan Chen. Welcome to IC Taiwan Grand Challenge Unveil. The IC Taiwan Grand Challenge is an initiative started by National Science and Technology Council, NSTC, to bolster Taiwan's IC startup ecosystem and to attract global tech talents. This is the fourth batch of IC Taiwan Grand Challenge, and we have selected 11 outstanding teams from 38 countries and from 209 innovations. Today, you are going to meet all of them on the stage. Before we begin, first, let's join me in welcoming Vice Minister Chen-Kang from National Science and Technology Council to deliver opening address. Let us welcome Vice Minister Su.
Yeah, so all the distinguished guests and the members of media and ladies and gentlemen, good afternoon.
Good afternoon.
We just opening 1 hour ago, and I believe that you can share very exciting experience here, and I wish you can enjoy all the phenomena of here of innovation. So it's my great pleasure to join the IC Taiwan Grand Challenge Award ceremony. As we may know, the AI is changing everything. And thus we are focusing on not only breaking through innovation made in IC design, chip application, but also the entire AI stack. Congratulations to the 11 teams which wins the IC Taiwan Grand Challenge Award. They are from the United States, Japan, United Kingdom, Germany, France, Israel, and Taiwan. You are so outstanding. We select you from over more than 20 teams from 38 countries. So you are the best of the best. Congratulations. So their technology are diverse and impressive, covering everything from chip design and IP to data centers, and even smart application for architecture and autonomous vessels. These 11 winning teams will be honored today at the award ceremony, followed by a series of presentations later. They will also showcase their innovations at the IC Taiwan Grand Challenge Pavilion, just next to this meeting room. And during the InnoVEX in the 4 days. But this is just the beginning. The National Science and Technology Council will provide the full lending support to these teams, which with local supply chain to linkage the local semiconductor whole ecosystem. And use Taiwan's world-class resource to validate and develop your ideas. Currently, AI is becoming the engine of our future. Taiwan already sits at the heart of the AI server supply chain. To stay ahead, our government is now moving forward with the so-called new 10 major AI projects. We are working on critical areas just like quantum, silicon photonics, robotics, and surveillance AI. Integrating computing power with real-world application to keep Taiwan competitiveness. NSTC will continue to build the best AI infrastructure and platform not only to culture domestic talent, but also to help more international teams grow deep root in Taiwan. Together, we will make Taiwan a leading AI island for the entire world. That's why the Computex and InnoVEX is entitled AI Together. So why we are here? In closing, I hope today's event inspires each of you to see the boundless opportunity the technology, innovation, and application have to offer. May today's event be a resounding success. And I wish you all the very best of health and every happiness in the days ahead. Thank you for your coming, and please enjoy your stay here. Thank you very much.
Thank you, Vice Minister Su, for your encouraging remarks. Please kindly remain on the stage. 您稍微留步. Ladies and gentlemen, it's time for the IC Taiwan Grand Challenge Award ceremony. When once again, let us introduce Vice Minister Su come onto the stage as our award presenter. 我们邀请再一次 please come onto the stage to present our award. And we will now announce the 11 winning teams, and each of the team is being called. Please kindly come to the stage and join Vice Minister Su to receive your award. So first, let us put our hands together to welcome Dallas Computing Inc. from the US. Please come to the stage, Mr. Jason Poon, the co-founder and product engineer. Congratulations to Team Dallas. Please join Vice Minister Su for the photo. Take the award. Please take up the award. All right. That's great. Okay, perfect. Look into the photographer at the back, waving at you. Show your best smile. 3, 2, 1. Perfect. Thank you so much, and congrats to Dallas Computing. We kindly ask you to step off the stage and to wait briefly for a final group photo. Second team, congratulations to Straight Industries from the US. Let us welcome Mr. Philip Ho, the co-founder and CEO, and Ballot Award, the co-founder and chief product officer, to come to the stage and receive the award. Congratulations to Team Straight Industries. All right, can I have the winners and Vice Minister Su to take a photo together? Look into the camera at the back. There is a photographer waving at you. Okay, move closer, move a little bit. 我们往右边移动一下. Okay, 3, 2, 1. Show your best smile. We got it? Perfect. Congratulations to Straight Industry. Kindly return to your seats. Next, our third winning team is Link from Germany. Let's welcome Dr. Samarth Vadia, the CEO and co-founder, and Dr. Laura Pretensik, the photonic design engineer, onto the stage. Congratulations to Team Link. All right. Do we have to move? Look into our photographer. Show your best smile. 3, 2, 1. We got it? Okay. Congratulations, Team Link. Kindly return to your seats for a little bit. Following that, let's welcome Caesarea Labs from Israel and welcome the consultant Christine Jing to come onto the stage and join Vice Minister Su. All right, 3, 2, 1. Your best smile. All right, thank you so much. Congratulations to Caesarea Labs. Kindly return to your seat for a bit. Now let's welcome RockCore Technology from Taiwan and welcome Chen-Kang, the Executive Vice President, to come onto the stage. Congratulations to Team RockCore. Okay, thank you so much. Please kindly step up and wait for a little bit. Up next, our sixth winning team, we would like to welcome Anya from France, Allen Chen, Director of Application Engineering and Business Development APAC, to come onto the stage. Congratulations to Team Anya. And thank you, Vice Minister Su, presenting the award. Show your best smile again, looking to a photographer at the back, waving at you. You can do a thumbs up as well. 3, 2, 1. Okay, congrats. Thank you. Kindly step up the stage and wait on the side. Following that, we would like to welcome Team Infiniflux from the UK. Let us welcome Team Infiniflux to come onto the stage. Congratulations to your outstanding performance. Show your most handsome smile. Look into a photo. We have to move to your left for a little bit. All right. 3, 2, 1. One more. Okay. Congratulations to Team Infiniflux. And thank you, Vice Minister Su, for our presentation. Up next, we'll have Thermalverse from the US, and we'll welcome Dr. Shantonio Burke, the CEO and founder, to receive the awards. Congratulations. All right, show your best smile. 3, 2, 1. Let's do a check. Okay. Congratulations to team, and thank you, Vice Minister Su. Next, we will have our ninth team. Let us welcome Leafy Lab from the US and welcome Ariel Yeh, the co-founder and CEO, to receive the award. Congratulations to Team Leafy Lab. Let's look into the photographer at the back. 3, 2, 1. All right, thank you, Leafy Lab and Vice Minister Su. Let's welcome Team TopoLogic from Japan and welcome Mr. Taiki Sato, the CEO, to receive the award. Please. Congratulations to Team TopoLogic for winning. Hold on. All right, congratulations. Kindly step on the stage and wait for a little bit. And last but not least, let's welcome Oculi from the US and Dr. Charbel Rizk, the founder and CTO, to receive the award. Show your best smile. 3, 2, 1. We got it? All right, please remain on the stage, please. 请留在台上. Doctor, please remain on the stage. And now can we invite Convener Conrad Yang from the IC Taiwan Grand Challenge Committee to join on the stage? And now once again, we'll invite all the representatives from the other 10 winning teams to join Vice Minister Su for a group photo to commemorate these very honorable moments. Ladies and gentlemen, presenting to you our fourth batch of IC Taiwan Grand Challenge winning teams, Vice Minister Su and Mr. Conrad Yang. All right, let's check the standing. 我们看一下这个站位 OK 吗？需不需要做调整？ I think we all have to. All right, is it good? 可以，好。All right, look into a photographer at the back, waving at you. If you have hands, we can do a thumbs up together, okay? We'll do a thumbs up. 我们可以一起比一个赞，然后看向我们后方的摄影师。Are you guys ready? Listen to my cue. 3, 2, 1. Thumbs up to IC Taiwan Grand Challenge. And congratulations to all the winning teams. All right, we got it? All right, thank you so much. And once again to the winning teams, and thank you, Vice Minister Su, Convener Yang. Please return to your seats. The IC Taiwan Grand Challenge is open for startups, university teams, and individual entries who focus on IC design innovations as well as chip-based application. And special attention is given to applications in AI core technologies, smart manufacturing, smart mobility, smart medtech, and sustainability. So first, we would like to introduce these teams to you, and they will come to the stage and present their solutions. First, let us welcome Team Oculi under the categories of AI core technologies and chips. The first team, they're gonna redefine AI vision at the age of fundamentally re-architecting how visual data is captured and processed. And once again, Dr. Charbel Rizk, the founder and CTO.
Okay, hello everyone. Thank you for selecting us. We're very excited to be in Taiwan. I have visited the island a few times, and every time I enjoy it even more. So make sure you select us again for another prize. You know, there are two strong words on that slide, fastest and lowest, right? So these are strong statements. And I can prove it to you guys that we do have the fastest and lowest energy AI vision in the world. It's a single chip that operates more like the eye. This is why we called Oculi the company, because it's Latin for vision. So I can stand here. So I don't know how many of you know that your human vision is 40,000 times more efficient than any machine vision technology today, even for a simple use case like detecting a person is present. Okay? Today, if you put a camera and a computer to detect a person is present, you spend 40,000 times more energy than your human vision. This is still how far we are from biology. And I'm happy to say that Oculi has a path to enable fast and efficient vision, because we built an architecture that you can implement in a CMOS chip that mimics the key aspects of the human vision, the eye and the brain combination. So that's basically what we're after, is building eyes or vision for machines. We developed this from scratch. And the first significant change that we're bringing to the world is moving from imaging, as you can see here. That's what cameras today do. Cameras are digital mirrors. They basically output a reflection of the scene, okay? But they have no intelligence on the sensor. Machine vision is not about pretty pictures. It's about getting the information very efficiently. And that's basically the difference between imaging and vision. So you have a lot less data on the right side, but it's enough to detect, to recognize it's a person. That's basically what we're doing now, moving from imaging that was developed for a different purpose to vision that's optimized for AI. So I'm going to show you a simple example, again, detecting a person is present. The world today has only one choice, which is to process a video on the left, and that's a lot of data. Our technology will basically reduce the data at the pixel level on the sensor itself and output only enough to detect and recognize it's a person, okay? We are able to do that with a single AA battery for a full year of operation 24/7. And that's an accurate solution. That's 99% accurate, so it doesn't have a false alarm. So the challenge really that we have today is that we always start with cameras today. We always start with capturing light. We capture light on the sensor itself in parallel, all at the same time, right? And then we end up doing everything in serial. So we digitize, transfer, store, all of that happens in serial, and that's what we call camera today. You have no intelligence yet. You went through all of that energy only to create the image. You haven't answered any questions yet. You actually, the next step is we tend to reduce resolution to run an AI model and output that a person is there. And that's the computing platform, okay? So today, to do visual intelligence, the world is stuck in these two platforms, a camera and a computing platform. And this is why machine vision today is expensive, slow, and power hungry. And we're reversing that completely. So instead of starting with an image first, we start at the pixel level, and we first sense if there's something there or not. If we sense something is there at the pixel level, we generate a little bit more data. And if we need more to answer the question, we generate more data, and then more data only as needed. So we are doing the reverse of what what we do on conventional machine vision. Because in vision, every pixel is actually the sensor, not the chip. The chip happens to be millions of sensors put together. That's the challenge for vision. So in addition to being the fastest and the lowest energy, we will always also be cheaper because our solution is implemented on a single chip. So you take our SPU, Sensing and Processing Unit, you put a lens on it, and that's your complete AI vision solution versus everyone else that has multiple components. So I talked about, I promised you earlier it's the fastest and lowest energy, and here's a real example. We did this field test for the US military where our single chip captured the flash from the gun. So what you're seeing on the right side is the raw output of our chip capturing the flash from a shotgun, okay? The sensor was running at 30,000 frames per second equivalent and only consumed 300 milliwatts. Those of you that work in the machine vision space, you know that it takes a lot more energy and hardware and expense to be able to do this use case. So that's the fundamental shift that we're bringing to the market. Today, we have multiple ways to evaluate our technology, and we're working with multiple companies here in Taiwan and across the world. And I'm happy to say that we are going to be offering our first product samples in a few months. So we get asked a lot where this technology is relevant. Well, I'm going to show you a few use cases that are important to me personally, okay? We still have cars today, despite all the AI and all the technology, that run people over, okay? Because cars today do not see pedestrians, right? The drivers have to see the pedestrian, right? Well, a good vision technology like ours would allow cars to immediately see a pedestrian and prevent that unfortunate accident. Another aspect of automotive that what's interesting to us is that the vehicle theft and vandalism is increasing across the world. This is actually a picture of a car that I know the person behind it. This is a brand new car that was purchased in Oakland, California, and this is how they found it the next day in front of their house, okay? Somebody liked the wheels, so they helped themselves to it. Okay, so cars don't have any vision, right? If you had vision, the car would see somebody is stealing the wheels and will sound the alarm, right? Another example that I found interesting, we still don't know how to automate the door, okay? Again, with all the AI buzz, automatic doors are still pretty dumb, okay? As you can see, this door opening and closing, even though nobody is actually going through, right? What most of you don't know is automatic doors waste $50 billion of energy a year because they open and close a lot more than they need to, okay? So think about that. Here's another one that's even a better example. This is an engineer that mounted this bear in their office to keep the lights on, because when you don't move and the lights go out. So they had to actually mount that bear to keep the lights on, okay? So we still don't have that level of basic intelligence in the room to keep the lights on, okay? What you probably don't know is that if we add smarts to control lighting and air conditioning, the world can save upward of $200 billion. That's a B, okay? That's how much we waste energy today by not having smart buildings. Okay, those of you that like to drink wine, you may be able to capture high-speed vision in the future with our technology. And this is by far my favorite example. We cannot automate a faucet effectively still in 2026. We're trying to build cars that drive by themselves, and yet we can't get a faucet that's smart enough to run the water when we need it, okay? So I showed you a few examples, there are many more, because the world today is visually blind, okay? Even your phone, right, has plenty of cameras, but it has no visual intelligence on board. And that's hopefully what our technology will do, is bring vision to many places. This is our team. I'm happy to have such a high caliber team. Patrick, our CEO, is here as well, and I have a colleague of mine manning the booth. I don't want to brag, but I can tell you I wrote the book about this problem for many years. I only started the company because I couldn't get anyone else to build the solution, okay? And again, we're happy to be in Taiwan multiple times. We've been recognized a few times, so we're happy to see it. Ultimately, you need real vision, not cameras everywhere around us to make the systems smart and efficient. Thank you very much.
Thank you so much, Dr. Rizk, for your sharing on Oculi. Thank you. Please kindly return to your seats. Next is the winning team from Japan, Team TopoLogic. They develop high-capacity cache memory replacement technology, allowing 5 to 10x of the cache memory capacity, increasing compared to conventional technology. Let's welcome CEO Taiki Sato-san onto the stage.
Thank you. So hi, we're TopoLogic. We're from Japan. So not too bad of a flight compared to all of the other contestants here from the US and Europe. And what we bring to Taiwan is we're bringing some material innovations. In Japan, we have a lot of material research. One of the material research that came out of the University of Tokyo that we're based on is topological antiferromagnets. Never heard of it. It's very new. We've been doing research since 2017, 18 for the material. And we decided, hey, we want to solve real problems with a material that has been mentioned. It's great science, but it's not going to be useful for any sort of application in the near future. And the problem that we decided to tackle is the lack of performance from AI chip processors today. Everybody's screaming that there's a lack of memory, there's a lack of supply, there's a lack of performance from these chips that either train AI, do inference models. Every single person in the supply chain says, we don't have enough memory. And so we decided, okay, can't we solve this problem with the material that we have? And that's what we're doing. We're developing a technology that is dense enough that you could cram, several hundred to almost a gigabyte directly on to the GPUs or the CPUs or the TPUs, whatever you want to call it, SoCs, microcontrollers, without sacrificing speed. We can meet speeds of up to 1 to 2 nanosecond read speeds, but at the same time, have the density similar to what DRAM, so like, HBM or main memory would provide. Significantly increasing the amount of memory you can put on chip. And what does that mean? It means you can process AI programs with 10 times more parameters, meaning more precision. And you can also train them with 10 times more data in parallel. So you're going to see drastic decreases in how long it takes to train a model with the same amount of data. And so this is what we're doing. So we're looking at this, you're looking at the memory tier. The world of semiconductors for memory is relatively simple. Now, if I say this, many people will get mad, but I say it anyway. You see, there's 4 tiers of memory in the memory space. There's cache memory, there's physical memory, and then there's storage, SSDs, hard disks, the ones on your laptops. We're targeting this top tier here, cache memory, because we know that we can meet those speeds. And because innovation hasn't occurred in this space for over 30, 40 years. We've been doing incremental improvement. Sure, we've been scaling, we've been making these incrementally smaller, but at the end of the day, we're still cramming in maybe 100, 110 megabytes of cache memory into a single chip, even today. And we have 64, 128 gigabytes of HBM. So a significant gap exists. And this is where we come in and say, hey, cache memory needs some sort of change now, because that's the biggest bottleneck in performance of these chips today. Now, right now, we're still in the prototyping phase, so we're still very bold. I'm very bold to say, this is what we're going to do. we're still prototyping on very mature process nodes from the 2000s. But this is a brand new material that goes into semiconductor fabrication. We've been able to integrate it successfully into 8-inch wafer processing with the support of the Taiwanese semiconductor ecosystem. We've started proving that our memory actually, performs the way intended to. But we still have a long ways to go. We plan to hit the mark in 2031. I'm not going to go into the details, but we're going to be focusing on scaling, where we need a lot more support from the Taiwanese ecosystem, because this is where all of the logic processor manufacturing is done. We also need to get them certified with the foundries. We need to get them, implemented into design tools today. And this is where, we come into Taiwan and say, hey, it's an innovation from Japan, but Japan unfortunately does not have a great position in the ecosystem today. And that's why we're here to say, that we want to bring this to the market together with Taiwan. Now, we also have the similar sensor technology using the same materials, but with a very, very different approach. So this is not an IC, this is not, but it's a silicon wafer-based technology. It detects heat very rapidly. This is a technology we've been working for about 5 years. So actually, this has been a longer business for us compared to the memory technology I explained. But it can detect heat hundreds of times faster than conventional thermistors, thermocouples, whatever you have in your smartphones or in your laptops today. What that means is that we can actually detect thermal runaway of batteries fast enough to actually prevent it. The thermistors in your cell phones today tell you, oh, we have a problem. And so they shut down the smartphone fast enough so that you'll realize and release your phone so that you don't get a burn on your hand. The batteries, the battery temperature sensors on your EVs, they monitor so that they give you enough time for you to get out of the car and watch your car perform a spectacle. Now we can detect these, incidents 30, 40 seconds faster than what those sensors do. Meaning that we can actually start to say, hey, please stop charging this battery cell because it's going to go into thermal runaway in about 5-10 seconds. And that allows companies, EV companies, to say, hey, we can actually prevent this from happening, and so we don't need the casing for it. We don't need safety margins as large as we need to today, leading to longer ranges in our EVs or longer battery life in our smartphones. Now, as of today, we already have, this is old, sorry, there's 14 partners to date, mostly in Japan. We are actually working with automotive tier ones already to put the product into automobiles, EVs, by 2029 with a mass manufacturing site with our partner company in Japan. So this is something that we want to implement into any device that is still, in danger of catching fire or in danger of, getting burned from the transistors, the inverters in those systems or from the batteries in those systems that, carry a lot of capacity, a lot of energy that could actually be harmful to you. These are some examples. I'm not going to go into the details, but a lot of our partners are in the electronics industries, automotive industries, equipment industries. So anybody here, working on, these components and want to say, hey, I want something so that, I don't have to worry about my battery cell catching fire or going into thermal runaway, so that I have more freedom to design. So because I don't need the casing for my battery cell anymore, or I don't need, additional safety measures for my battery anymore. So let us know. We have prototypes and we can, custom build sensors for you, and we can work on that from tomorrow. So that was my presentation. We're always looking for partners for our memory technology. We're also looking for companies interested in using our sensor technology and have the applications or products that they have. And you can reach out to me on any of these contacts. Just let us know. And we'll fly in 2.5 hours and get into a meeting right away. Thank you so much for your time, and we'll meet you at our booth.
Thank you so much, Mr. Taiki Sato, for your presentation on TopoLogic. Please kindly return to your seats. Next is the winning team from the US, Leafy Lab Inc. They pioneered agentic design optimization for the semiconductor value chain, building tools that enable autopilot for chips. Let us put our hand together to welcome co-founder and CEO Ariel Yeh. Okay, she's already on the stage. All right. You can begin when you're ready.
Thank you. Yeah. So huge thank you for the organizer, the committee, and the Leafy Lab team. I'm very excited to share with you Leafy Lab. We are an agentic AI platform that help optimize from chip design to manufacturing. And we aim to save time to market by more than 50%. Our founding team are fully deep tech engineers. We are at 9 people today. Me and my co-founder are from PhD from Harvard and MIT. And my co-founder is also associate professor in United States in electrical engineering. And myself as a serial entrepreneur, this is my second startup. The first one went IPO in NASDAQ in 2.5 years. And I can't be more thrilled to be back to building startup and closing the gap between AI and chip design. What Leafy really differentiate in this market, in this very complex problem that we're solving for in chip design and manufacturing workflow, is accuracy, execution, and our expertise. So in terms of accuracy, our model has already outperformed standard models such as AutoML, and we've been recognized at Design Automation Conference and other recognition, such as today. The execution is very strong. We have multiple paid pilot projects, including top 10 chip design house that are building AI chip today. And we also are backed by US Silicon Valley VC. Our expertise is really the reason why we're so excited to be here. And we actually have very cross-disciplinary talents from 3 areas: enterprise software, experts in AI and machine learning, and also our analog and IC designers. And this is why we can come together where everyone may not know what each other are doing, but we come together and work together and to solve this problem. So today, we are really in an accidental crisis. The first time of a chip being successfully fabricated is at all-time low. And leaders are asking, how can AI help build a chip, not in 3 years, but in 6 months? And that's exactly what we are helping. And yesterday, we heard Jensen Huang saying that agents is already built in, but the agents are currently building for their front end of chip design. We are building the back end that feed back to the front end. And that is a physical design that we believe to be the most challenging to automate and apply agentic AI. So the market is huge. Everyone here believe that it's going to reach 1.6 trillion in 4 years. In fact, Leafy plays in that 200 billion market, and that includes software, verification, and IP. What we want to build is a unified intelligence system for the entire semiconductor value chain to work together, not with contract or multiple meetings and communications. They can have better models to streamline and to accelerate this chip to productions. So what is our technology? We think about our technology also in layer by layer level. So we start with device level. We have AI to predict how a transistor will behave in current and voltage curve at very high accuracy. We go up the layer, we go into layout and circuits. And in terms of the technology of our core, we start with domain. So we have designer constraint, designer intuition with historical fabrication data. And we wrap that around with automation AI. So our AI actually is explainable, meaning that is, for example, a neural network type of AI will allow the engineer to understand the sensitivity of their design. And then finally, the product is where we differentiate. Currently, the designer are still using a 40-year-old product, and it's heavily manual and also limit their innovation to find global optimizations. So very glad to share with you that we reached several business metrics, and that includes a 3.6 times performance improvement when we compare our platform versus a traditional approach. And that's because we apply automation and agentic, which I will share in this slide. So the top workflow is the current approach, where every single step is scattered, and every stop, you need to check whether you pass DRC rules from foundries. If you don't pass, you go back. And so that is why you only start stuck in the local optimization problem. And what we are doing is we combine 6 different software that is currently being used today with automation. And on top of that, we train our model with those data. So we have enough data points to train a really good model. I am not able to share the video, but I encourage you to stop by our booth just next door. So this is the screenshot of our product. Immediately, you can see that 2 things. It's very intuitive. As an analog or IC designer, you come in with your blueprint, and you ask the platform to execute your blueprint or tell you if your blueprint cannot meet the spec. And then secondly, through each of these optimization rounds, we actually are reaching a better PPA, power, performance, and area. Another product that I mentioned is at the transistor level, the single building block of chip. And we already saved more than 6 months of chip design house time because our model is their final tape out. They don't require another respin when they have model predicted what the fabrication run will look like. And that was recognized, and we are peer review in design automation conferences. So another demonstration how we really prove our accuracy, we benchmark with other type of models in the market. And comparing MRE, mean relative error, we're at the lowest, meaning we're the most accurate across training and testing. And most importantly, when you look at the actual data number, it's only hundreds. In the big data world, everyone is talking about machine learning training on big data. There's no big data when every fabrication is so expensive. So our model is very unique. The workflow actually can optimize for small data as well. Finally, I want to leave you with where Leafy is going. So we started with one of the hardest problems we believe, which is in analog chip design and fabrications. We are going into silicon photonics and 3D design. And eventually we want to reach and close that gap to physical AI, where everyone is so excited about building robots and building the most complex design for the world. And thank you for your time, and happy to talk later. Thank you.
Thank you so much to our amazing female founder, Ariel Yeh from Leafy Lab. Thank you. Please kind of return to your seats. All right, up next, we have the winning team under the category of sustainability. First is ThermalVerse Inc. from the US. They tackle and escalate energy costs of commercial buildings in AI data center host communities by transforming the unmonetized negative space of drop ceilings into the world's largest visual power plant. Let's give a warm round of applause to founder and CEO Shantonio Berg.
What if I told you that the world's biggest battery is hiding in plain sight, right in our buildings? Hello, everyone. I'm Shantonio from ThermalVerse. We leverage thermal energy storage to unlock faster, cheaper, scalable grid capacity. Just how much? A Tesla megapack's worth. Enough energy to power 40 additional EV chargers on a 100,000 square foot commercial building, or power the world's largest virtual power plant at 100 terawatt hours. A little bit about me. My story and the genesis of the company started out as a PhD engineer at the University of Michigan facing heat stress. Since then, I've raised $1.3 million in significant non-dilutive funding, secured 2 patents for the world's most compact technology, which is a thermal energy storage that I'm going to talk about later, and first revenue within the first year of product development. The real problem that we're actually addressing here really centers around data centers. Data centers by this year will be consuming the same amount of energy as 100,000 US households. And the folks who are going to be impacted by it the most are not the data centers themselves. It's the building owners. It's the residents, it's the municipalities, utilities, you would have to shoulder the cost of AI expansion in the form of increased utility bills as much as 267%. Now introducing LATCHES, the world's most compact thermal battery that can be integrated behind the meter to manage the largest energy consuming asset, which is your heating and cooling system, or your HVAC. The technology promises faster, cheaper, and scalable capacity. And let me tell you how we get there. We leverage smart controllers to basically intelligently move heat so you do not have to rely on the energy-consuming HVAC system as much. To this, we have tunable thermal storage, essentially the same materials that you use to de-ice the road in the winter, leveraged to basically maintain temperature set points rather than using the HVAC system consistently. Lastly, and this is the biggest value, we offer seamless integration with the existing built-in system. That includes a built-in automation system for easy installation, but also to enable some more advanced building control strategy, like time of use optimization. The technology can be compared to some other technology that's out there on the market. We're probably like some passive thermal tiles that they make, but we're very different because we leverage the thermal PCMs to basically create an active thermal storage solution as a thermal battery. We're probably more like these dispatchable thermal asset, these grid scale storage, but we are very, very small. We're dispatched right in the ceiling, hidden in plain sight. I'm happy to share that we have a small scale pilot demonstration in downtown Detroit, a market of 19 million square feet retrofit potential, and we have validated 20% energy reduction as a standalone system. The typical ROI for the customer is going to be 15 years, but the tech is not meant to be a technology that is standalone. It's meant to be tied with the HVAC. It's meant to be tied with something known as a built-in automation system or the BAS system, where we have already done the hard work. By simple software, we can drive step change improvements in HVAC efficacy, taking the system from 20% to 60% and delivering an ROI for the customer of 3 years, which is on par with LED lighting retrofits. The market size is huge. It's smart buildings. It's a $164 billion market comprised of new construction and retrofits in the US. We're going to be targeting the first 50 million comprising of commercial buildings that are impacted by AI data centers. Our go-to-market is centered around B2B sales, equipment sales, also tag along with the energy management as a service platform. And we're going to be targeting 3 unique areas. We're going to be targeting folks within the Detroit Edison area, Con Edison, that's New York City, and the data center capital of the world, which is Virginia. We're going to be targeting commercial buildings that are within a 50-mile radius of a data center activity. And we're going to be showing how our customers can leverage that 1 megawatt hour capacity to do more, such as charge 40 additional EV chargers, or to power data centers, or to deal with some of the fines that they have, like in New York City, Local Law 97. In all of these 3 cases, we're going to be partnering with utilities to provide highly discounted pilots for our customers. Then we're going to produce and distribute to grow within their portfolio. And then we're going to aggregate demand using energy management as a service. I'm happy to share that we are on a very consistent growth trajectory. We have paid pilot demonstrations, and we're expanding our sales pipeline across Michigan, New York, and Virginia. That 10 million ARR pipeline. We have our patent file sealed and delivered, and we're waiting applications, prosecution in Japan, China, and Europe. We are industry leaders. We were bronze sponsor for the Thermal Management Expo, and we were awarded and recognized the Small Business Minority Award by the state of Michigan. The path forward for us is a $3 million pre-seed. 40% of that is going to be used to build out our energy management as a system software platform. 35% is going to be used to reduce the cost of goods for our product, and this is where Taiwan comes in. And 25% is going to be for new customer acquisition. Overall, we're going to be validating that we can reduce the HVAC load by 40 to 60% and reduce the IC cost of good by 40%. And then we want to triple our customer pilots that we have. All this is in an effort to unlock the first $1 million in revenue. We have a stellar team. We have 1 seasoned HVAC professional who have installed advanced HVAC sales buildings in Mango buildings. That's Meta, Apple and Google. We have 2 manufacturing and supply chain engineers on our team. We have 3 certified build and performance analysts. And we are together a team of 5+1, including a sales professional who have built go-to-market engine within 3 years and built Xiaomi's $10 million pipeline. And we are all united under one mission. How do we leverage thermal energy storage to unlock faster, cheaper, and scalable grid capacity? A Tesla megapack's worth. Thank you.
Thank you so much, Antonio, for your sharing on Thermalverse. Thank you. Please kindly return to your seat. Next team is Infiniflux Ltd from the UK, and their topic is scaling compute sustainably with the next frontier chip cooling. Let's welcome CEO Marc Ottolini onto the stage.
Hey, good. Good afternoon. My name is Marc Ottolini. I'm the CEO and co-founder of Infiniflux. We bring chip cool, breakthrough in advanced liquid cooling for AI chips. And let me start with, if the button works, yeah, here we go. I'm here with my co-founder, Bernard Cooper. Bernard did his PhD in cooling for quantum computing. And when we met only 15 months ago, we decided that the market wasn't quite ready for that, but that there was definitely a market crying out for a solution, which is AI chips in data centers. I myself have a track record of both working in a corporate environment with Philips Electronics for many years, and then many years of startups and scale-ups that has ultimately led to Infiniflux. And so we are a perfect combination of gray cells with gray hair. We're being advised and supported by a large list of people and corporates in the AI supply chain. So I won't dwell further on that, but let's focus on what is the problem that we are addressing. What you see here is that almost every year, the power per chip is going up significantly. But what this graph is also showing is that the power density, so the watt per square centimeters, is flatlining. And why is that? That is basically because of the fact that there is currently not a capable cooling technology to remove heat fast enough from the dies inside these chips. And as a consequence, the only way to increase the wattage per chip is to make the footprint of them bigger. And you see that with the latest NVIDIA chips that are starting to become really big. Well, if you would project that forward, yeah, who wants to have a chip the size of a football field? Yeah. So it's a major issue, a major cost issue, and it can only be addressed by increasing the heat removal capacity. And that's where we come in. If you look at how currently AI chips are being cooled, it's primarily being done with what is called single-phase liquid cooling. So that's the picture on the left, which is basically a piece of copper where water is flowing through it, but that copper piece sits on top of the chip. And so there are several layers between the liquid cooling and where the source of the heat is, which is the die inside the chip. So there's a massive heat resistance there. With our technology, which we call direct-to-die two-phase, we do two things fundamentally different. So the first thing is we sit directly inside the chip, right on top of the die. So direct contact with the die. And secondly, we use two-phase cooling, which means that we use the heat of the die to convert a liquid into a vapor. And with that, we can transport about 6 times more heat per watt of cooling energy. So there's a massive energy saving, but more importantly, by having a thermal resistance that is 75% lower, we can remove the heat from the dies much faster, and in particular from the hotspots, which are the critical point in those dies. There are a few companies that are trying to go even further, where they want to go with liquid cooling inside the dies themselves. We call that a bridge too far. And the reason for that is that although the thermal resistance in their case is more or less comparable with our technology, the amount of energy that they need to get the liquid through and remove the heat is many times higher than ours. That doesn't make data centers happy, because data centers are looking at the energy bill, and they are looking for ways to bring that down rather than up. How do we achieve this very extraordinary performance? That is basically by doing a couple of things. So in the first place, by bringing the two-phase liquid very, very close to the interface with the silicon die. We then have an alignment of the most powerful points of the cooling system aligned with the hotspots of the dies. Because it's all about the speed with which you remove the heat from those hotspots. And by doing all of that, we achieve a level of performance that is not possible with any other approach. We call this basically the sweet spot of the hotspot. And you see this back also in this graph, where on the horizontal axis you see the amount of energy needed to remove 1 kilowatt of heat, and on the vertical you see the chip temperature. So we are really in that sweet spot of the lowest die temperature. And it's not just the average temperature, but it is in particular also the uniformity of the temperature of the die. And we are also the lowest in energy per kilowatt of heat removed. So this makes both the semiconductor companies as well as the data centers very happy. We see basically both short-term effects of our technology and medium-term effects. So if you look at the short-term effect, so basically applying our technology to chips that exist today, we can achieve for data centers about 25% free compute. Basically, we can support sustained clock frequencies much higher than is possible currently, and that gives a data center a massive income bonus, basically for free. Secondly, significant OPEX savings, 20% or more, not only because of energy savings, but also maintenance savings. And then thirdly, we give more than double the lifespan of the hardware. And that is a cost benefit that is absolutely huge. If you look at this example of a 100 megawatt data center, where the IT equipment capital investment is about 3.5 billion euros, we save over a 3-year period between 1 and 1.5 billion euros. So our payback time measures in months rather than years. But there's also a medium-term benefit, and that is we can use the extra thermal headroom that our technology provides to bring that back into the chip design rules, and that can then be used in a number of different ways. And one of those is to significantly minimize the footprint of the chips. Secondly, we can go for really using it for achieving extreme high teraflops per second. And thirdly, we can also use this to enable vertical 3D integration, where we can combine very hot CPUs and GPUs with heat-sensitive components like the HBMs and also the optical components that are increasingly going into these chip packages. Why are we here? Because in Taiwan, there's a unique situation of having pretty much all the players in the entire value chain, from chip all the way to data centers, down here. And that is exactly what we need to demonstrate the impact of our technology. And that's also why we are seriously interested in setting up a establishment here in Taiwan. We're supported by quite an array of important players, both on the financial side as well as on the operational side. In particular, we're working with the largest AI infrastructure investor in the world in Saudi Arabia for setting up a test facility. And if I just finalize with what we're aiming to do here in Taiwan, it's really to work with the ecosystem to get our technology adopted, which will give the Taiwan semiconductor ecosystem an additional competitive advantage. So I see this as an opportunity for partnership, and we hope to get support both from industry as well as government and academia to make that happen. I'd like to thank further the NSTC, ITRI, InnoVEX UK, and the British Office Taipei for their support. They've been fantastic for us so far, and I hope that we can count on your support in the years ahead. Thank you very much.
Thank you so much, Mark, for your sharing on Infiniflux. Thank you. Up next, we will have Ania from France to come onto the stage. OneCheck plus Amigo AI is the former ERC platform for analog and mixed signal sign-off, augmented by the autonomous AI design agent. Let us welcome Allen Chen, Director of Application Engineering and Business Development, APAC.
Good afternoon. Grounded AI agent for Tape-Out ERC. ERC is electrical rule tracking. It's the most important verification task have to do for Tape-Out. So now for advanced mixed signal Tape-Out, now the verification engineer now is the bottleneck, not running the tool. The verification engineer is the bottleneck. I'm Allen from Anya. It's a EDA French company. So our platform providing 3 options. OneCheck for formal coverage, Amigo AI to explain the result, and we can work with other sign-off tools to run spice to get evidence. So today I would like to show you 3 things. First is why your verification engineers are bottleneck, and how our engine fix it. And now we are working with the customer deployment. So here is a problem with the 4 number, 40%, $40 million, 41%, and 47%. 40% is about how often the chips work for the first try. 86 out of the 100 will have to respin, and $40 million for the spin cost at the TSMC N3 process node. 41%, the third number, respin come from the mixed signal and the analog bug, not digital, it's analog bug. And the final number, 47%, is almost half of the verification time goes to debug. not running a test, not running a tool. So an engineer staring at the screen, deciding which is the true problem, which is the false positive. Nowadays, the AI interface, every new interface, chiplet, power domain you add, the review time doubles. So now your verification engineers now is the bottleneck for Tape-Out. So why has nobody fixed it? Because every current option breaks in different way. The first one is a static ERC. Static ERC will report a warning, a lot of the false positive. So a real problem will be buried under many positive. The second one is the two running spice simulation. Run spice simulation can get a correct answer, but with many power state, we cannot run it for everything. The third option is related to EDA Copilot. It's AI, it can read the text, but generate more text. Actually, I will use it for the mail draft, but not for the Tape-Out ERC. Because there is no electrical truth. Our solution, our angle is narrow and variable. We provide one platform. One platform, we keep the reliable and formal coverage, sign of you trust. And to remove the manual effort that by each engineer's time by leverage the grounded AI. So the key point here is we are not only providing the sign-off tool. We building sign-off tool top on other sign-off tool to have their output easy to review and easy to audit. So it's Anya's 5-layer cake. So there's 3 critical parts. The original part is the OneCheck, is our foundation engine. We know circuit very well, so like circuit topology, power state, and the power domain. The green part is Amigo AI. We try to leverage all LLM model to ask a question about the violation. There is a tool boundary in between because we don't want to have the AI meta answer for the report. So here is our workflow. First, we will generate a violation, and the first step will group as a cluster. For the cluster with the same root cause, consequence, and the power state, and go to the second step, we will generate the spice test bench to run simulation. And in the last step, we will get a true answer, compare against the AI report generated by the first step. So what user can read is the report with the evidence. Okay, it's the real customer example. It's a true error, and we found the true error. Other tools cannot find. There is the purple net. Is the highly node. It is a 14 node and the comma root cause for the current leakage. By the way, this color is annotated by the OneCheck. It's a unique feature for user to review. The greatest part here is we can make the reviewer action to the review memory. So it will become the context for the next design review. The marketing is going on our favor. With these 3 numbers, the first one is $5.4 billion is electronic system design revenue. Almost $700 billion for the 2025 sales. It will be record high this year. The third number is $150 billion for the genetic AI chip. And actually, all of those chips are very complicated mixing or design. So while we do ERC first, the pain point is urgent, and the workflow is well defined. And we can always find a stakeholder to manage the tape-out risk. So it's our business model. We have a 3 steps. The first step is land. Land with the pilot project with customer. Second is the production license. The 10 deal for the 1 year, 2 years after prove our value on the pilot project. The final step will be expansion. We will expand our license usage application by application. Okay, it's a roadmap. So we would like to turn engineer review into an auditable operating system. So from now to 1 year later, they will be very different for the sign of flow. So it's my last stage. Here is the ask. We would like to ask for the pilot customer in Taiwan for 5 Taiwan semiconductor player who manage the advanced node tape-out risk, and the partner for the workflow partner with the EDA vendor and the foundry vendor for the new lower deck developer, and the strategic capital with the well-defined 1 year milestone. So ANIH, actually ANIH is a needle in a haystack. In Chinese, we say 大海捞针. So we find the true error under hidden noise. If you have any question about the ERC tape-out, come talk to me. Thanks, Alan.
Thank you so much, Alan, for your sharing on Anya. Thank you. Up next is welcome RockCore Technology from Taiwan. Your topic is powering next generation defense and semiconductor equipment through advanced hardware design and proprietary FPGA IP. Welcome Project Manager LIU KENG WEI.
Hello everyone. Good afternoon. I am Keng Wei, and I'm also a Christian, and I'm in RockCore. And the most important thing is I'm a Taiwanese. I'm really glad that I can represent Taiwan to get this award. So thank you. And today I want to share with you about why we do this startup. You know, I have been in semiconductor industry for over 10 years. I know that I can be a consultant, I can be a coach, but why I choose startup? Because startup is just do it. We found the bottleneck, so we want to empower, use the generation for our semiconductor industry. So the most important one is we have to accelerate and also empower our equipment to be better. So that will be make us our, not only for quality, but also our UPH will be increasing. So that is what we did, is we use FPGA to deal with that. So I think Taiwan is not only an AI island, but we are also a semiconductor island too. So what we did is we connect AI and semiconductor together. That is our ambitions, and we are also on the way to do it. But by the way, we also focus on defense because, you know, some political issues, we're islands, so we have to focus on defense. So that is what we are doing. So now let me show to you about what the bottleneck and what I see in the industry we face. So first one is GPU. Okay, I think Jason, yesterday I mentioned about some GPU things, but now we just want to tell you about what our customer facing in the bottleneck is the GPU latency. It's not quite a little slow. So what they wanted is want to save their time. Time is really important. No matter how it will be to have 50 milliseconds. Everyone will think it really fast. But however, they want is 10 milliseconds or 20 milliseconds. They want to reduce lower, lower, and lower. So GPU latency is quite a little bottleneck in our industry. And second part is IP issues. You know, about now, the software in PC is easy to copy and paste. So everyone will care about, wow, it's easy to copy. We cannot take it to be really protection. So we want to find a solution to fix for that, to deal with it. And the third part is legacy friction. Now we see about our equipment, you know, in factory in Taiwan, also in Asia, we have long history for the equipment and also factory. So the machines are old, and also the talent are not focused on how to do it, make it better. So now the old machine still old. How we can make it in power? So that is what we did. We use FPGA to do that. So next step, I will show you by a golden circle. Why, how, and what. So that can see what we do. So what RockCore do is we use hardware. It is a moving AI form from software and cloud to hardware. So how we did it? We use FPGA. FPGA is a hardware we're developing, and we use our programming the AI algorithm into this FPGA, this IC. So that can make everything quickly. So that is what we do, and we'll show you how we did it. So how we did that is our domain know-how. What we do is heterogeneous core architecture. So first you can see about the first layer. What we did, we used the hardware to write down the algorithm inside. We program it inside, so that can also protect it. And also what we did is hardware to do the algorithm. So it's really quickly. They don't have any time to spend any time to do that. So we can make a time from 80 milliseconds to 20 milliseconds or 10 milliseconds. So that is what our important things. And second part is SoC with FPGA integration. So FPGA is really, really fast. Everyone knows that. But how to integrate? I think in Taiwan, we are really focused on and really famous for IPC, just like Advantech. They're really familiar how to use x86. But x86 is also in CPU. So how to integrate CPU, GPU, and FPGA? That is a gap. So we are the key man to deal with that. We can integrate FPGA to let it easy to have platform to integrate and also to programming in that. And that will be easy to deal with everything. And the final thing is that we found a high precision vision. We can get the vision into our FPGA to deal with that. So all the things we provide is not only a sensor, not only FPGA. What we provided is a total solution to deal with those customers who can deal with that. So why we did it? So you can see the comparing table. The left one is the old CPU, the software what it did. So response time, I've shown you that will be for seconds, but we are for a millisecond. So we are ultra low latency. And second part is IP security. So vulnerable software layer is what I think x86 were also like in ARM-based also face the same situation. But if we write the algorithm into our FPGA, everything keep protection perfect. So that is security we can do for customers. And last thing is industrial performance. So we can see about the high software certainty about x86. So I think everyone, I don't want you to raise your hand. Your PC, your notebook have some lag, but in FPGA, we don't have it. Because FPGA is also not for low latency, but they are low power consumption. So our FPGA, the heat is also can maintainable. We don't need a lot of heat and also low power consumption. So which means that we can make everything stable, especially in semiconductor industry, they need it. That is a really important thing. So for our product, we already did for success story and reference in Japanese market. We have also tagged the market in Yoshiro Group. This is focused on photography machine. The company is Editech. They also use our algorithm of FPGA to deal with the accelerator layer product to link it. Before, they also use CPU and also easy software to deal with that, but now they use our FPGA, which is faster and also accurate. Yeah, and the other hand, we also have a project in defense-related system. We already designed in, so just for example, you know the missiles, they can wait you for a second. So we have to need a millisecond to check in the missiles and deal with that. So that is what we did, and also we have the success story. So the component to ecosystem is what we did. So the domain know-how for our core value is we have a embedded high-speed image processing inside. That is also make our equipment be better. And second part, we just broadened to use like an standing environmental monitor. We use 360 with the AI FPGA inside to do the tracking whole the factory. So we are not only focused on inspection, but also we can control and monitor all factory to do really an AI factory. And in future, I think maybe 2 years later, we'll do is for digital twins. That will be can read real time and also with AI agent and can deal with everything in the factory. So that can make our semiconductor industry really, really good in all things. Quality will be increasing and also time and UPH will be increasing. Both increasing can make us being really a semiconductor island. Okay, so I think this time I really appreciate for Taiwan. Yeah, because Taiwan provided us a lot of resources. So you can see we have a research institution, ITRI. Our company is being from ITRI. ITRI is also our talent pool, can provide us really a good talent to let us to design this FPGA. And also we have IC design companies a lot, like Novatech and also MediaTek. We are also famous on IC design. And last, we have industrial PC partner like Advantech. They provided us a really stable and really high performance PC to let us integrate this FPGA inside. So while we have the new terms, we are not only AI PC, we are stand at the Jason's shoulders, we are AI FPC. So next generation for us, we not only focus on FPGA, but if we have some quantity and quality, we can also focus to next generation. We can use ASIC. It will be more faster and cost will be downer. So that is also our next step for in this industry we can do, and also our roadmap. So finally, this is our business model. We sell hardware sales and also IP licensing, and then we can do the smart solution in factory. So that is the total solution that we can provide it in semiconductor. So that is why we connect AI to semicon. Yeah, so as I say in the beginning, this startup is not only earning money, and we are not only consultant, and we are not only for coach. What we do is what we just did it. We just do it. We do is we want to build this foundation. We make our customers increasing their UPH, make it faster, and we use algorithm in our FPGA that can do more, so we can more precise and more secure. So we are RockCore. Thank you for your listening. Thank you.
Thank you so much, Mr. Liu, for sharing on RockCore. Next is the winning team from Israel, Caesarea Labs. They will share semiconductor post-silicon validation, EDA, and welcome Christine Jing onto the stage.
Thank you, Taiwan. Thank you, God. Hi, Connor. Hi, Aviv. Hi, everybody. This is Christine Jing. This is Christine Jing, the consultant for Caesarea Labs. Caesarea Labs is a semiconductor EDA startup focusing on post-silicon validation. We develop software to help chip makers improve physical validation and testing. Today, post-silicon validation is still a major industry challenge. This slide shows the complexity that will increase high cost and a longer cell development cycle. Our CEO Marc experienced this challenge firsthand at Intel, where flagships named Cannon Lake suffered major delay, and delay eventually canceled. That's because a heavier post-silicon validation. This page shows the post-silicon validation is in the ecosystem. which deserve to get your attention. Because if there's a problem fall into the post-silicon validation segment, it will become a bottleneck, then has to be manual tested, have to manual solve it. So otherwise, for other segments, already have a good EDA coverage, then dedicated system. That's why we like to enable the scale and the productivity to suit for this continuous raising complexity. Okay, a common question to us, why not solve everything in pre-silicon validation stage? The reason is simple. Simulation cannot fully reflect the reality. For example, car industry still rely on the crash test and the test driving. Semiconductor chips are even more difficult to fully simulate. This slide shows post-silicon validation has become an issue. By 2020, you can see the post-silicon validation cost grows from 2%, jump to 20% of total chip development cost. Since the process is highly still manual, chip makers has to hire more people, more resource, and more time to prepare before the product launch to the market. Okay, we talk about the problem. Now it's time to talk about the solution. I'd like to introduce Caesarea Labs, the first dedicated post-silicon validation EDA company. We aim to bring modern capability to this segment. This is Caesarea's founding team. Marc, Noi, and Ole Sharmai, they are both Intel alumni. Marc, our CEO, is an expert in post-silicon validation with deep industry and market knowledge. Ole, the CTO, is an AI and an EDA specialist with very strong expertise in both semiconductor validation and software development. He is also previous lecturer at Tanian, the Israel equivalent MIT. Together, the team combined post-silicon validation expertise, EDA software capability, and the industry experience to solve this critical challenge. Okay, this is the competition slide. Although there is no established company fully focused on this area, chip makers are focusing on the test, on the chip development and also test. Now building an EDA infrastructure, then establish the EDA company. They both mainly focus on the design and the pre-silicon validation since the 80s and 90s. Today, they still remain focused on their existing market and also apply new opportunities such as chiplet, advanced package, and AI-driven design. Then Caesarea Labs is the unique position because this problem requires EDA expertise, industry knowledge, and post-silicon validation. Okay, our vision starts with automating circuit edit. This is to speed up chip testing and validation. You can think about the engineer can use FIB tools to modify chips at a nanometer scale. This helps fast chip testing without manufacturing a new chip. This slide shows the workflow we are automating circuit edit. Our MVP already automated circuit design and demonstrated. Then our longer vision is to automating the entire circuit edit flow. Finally, this is our product stage. Here is the sneak peek of our product. It includes our own 3D chip layout viewer and also circuit edit automating software. The colors Remark shows different edit in 3D. Okay, this slide shows the benefit of our product. We can achieve up to 100% times faster circuit added design, up to 10 times cost reduction, and almost 100% successful rate, and the 3 times higher demand for the circuit added services. Oh, here's our market forecast. The circuit added market yearly can generate around 100 million revenue. For longer term, they plan to expand into the broader post-silicon validation segment. This represents a total market opportunity around $8 billion. Okay, this slide shows the longer growth potential to be a next generation semiconductor EDA company. Like other semiconductor company, we expect a slow start because of the long sales cycle and the industry adoption. We expect to accelerate the growth when our solution gain industry recognition. We are asking for 5 million seed round to help us to accelerate product development and also POCs. We already raised 30,000 investment. Our longer-term vision is to acquire in 5 to 7 years. The recent EDA exits have reached our multi-billion-dollar scale. We believe Caesarea Labs has a unique position in a new and underserved market. Okay, that's all for my presentation. Thank you.
Thank you so much, Christine, for your sharing on Caesarea Labs. Thank you. Next, we have a team from Germany called Link. Link is a deep tech startup based in Germany building the next generation of AI and cloud infrastructure using their disruptive program Silicon Photonics technology for information progressing. They are also part of the Germany-Taiwan flagship research cooperation between NSTC and Germany, a Ministry of Research and Technology. And I see Samarth Vadia already on the stage.
Great, thank you. It's a great pleasure to be here. My name is Samarth. I'm the CEO and co-founder of Link from Germany. As pointed out, it's a great honor to be part of the IC Taiwan Grand Challenge. And I'm going to tell you about what you see here in the center of this slide, right? So it's an IC, but it's a special kind of IC. It's a photonic IC. So the data is not in electrons, but rather in photons, in light. And why do we do this? This is what I'm going to tell you about in the next 8 to 10 minutes. But before I do the talking, I would like to maybe start with asking you guys a question. You have been very patiently and very nicely hearing all these brilliant startups. And we know the Vice Minister already pointed out, the talk of this event is AI, right? So how many of you have used ChatGPT, Claude, or some similar AI service in the last 7 days? Can I do a quick show of hands? I want to see if AI is really that impactful. Yes, I see most of the hands up. So it is really a transformative technology that we have been talking about and knowing about over the last few years. And that reflects in one of the most immense, let's say, investment or infrastructure build out in the history of humanity, right? Some of the hyperscalers are spending in the order of about $1 trillion in just the next few years to build the data centers and other compute infrastructure, right? But building the compute infrastructure also comes with the challenges. And the biggest challenge is the energy consumption, right? Several other startups have pointed out, but we also talk about it when you look at a keynote yesterday from Jensen, right? And the solution to energy consumption is not that we start building data centers in space or we find ways to keep going in crazy ways. The solution is to reduce this energy consumption, find hardware, find solutions that can fundamentally limit this. And the focus of us using photonics is on the network stack of the data center. Why am I going to talk about the network stack? When you look at the data center, there are 3 kinds of hardware. There is the compute, like the GPUs, there is your memory, and then there is the network stack. The network stack actually has become one of the most critical layer, actually. And a very intuitive reason to think about that is that we have von Neumann computing, right? So the memory and processing is separated. And when they are separated, you need to transfer this data between the 2 domains, right? And when you do that, you need networking stack. And now that we are using these very large models, the LLMs, we are not computing on single GPUs. We are computing our models across thousands or even millions of GPUs at the same time. And what that means is that the network becomes even more critical. And that's kind of the numbers you see on the left side, right? If you look at the energy consumption it takes, but even if you go to the ground floor and look at the NVIDIA rack, right? 2/3 is the processing and 1/3 is the network. So that's kind of the role that network plays right now. And that also reflects in some of the technical requirements that this network needs. Right, so what is our solution? So let me first tell you about the product. So what we have built is a new kind of switch. If you go to the data center right now, if you visit your AWS, right, what you will find is the switch from your Cisco or NVIDIA, which is all electronic switches, right? Your Ethernet or InfiniBand. But what happens is that you are sending your data via light, but all of the switching is happening electronically. So you are always doing this conversion of data between optics, electronics, optics, every time you pass through a network node. And this is a huge overhead which you can totally avoid. So that's what we do based on our photonic chips. So our product is a rack unit, optical switch, and all optical switch, which does not require your data to be converted to the electronic domain, right? And I will not tell you about all the intricacies that is related to the optical switching, but the bottom line is what you see on the right side, right? So if you compare NVIDIA CPO switch that is coming out to the market next year to our link rise, we can reduce the power consumption by 20 times. The CPO switch takes 2 kilowatts, we can do it for 100 watts, right? And as a network operator, what you care about at the end of the day is your OpEx, and that you can, of course, save by, one, reducing your electricity cost, but also your cooling cost. So how do we do that? So at the heart of our optical switch is a photonic integrated circuit, right? I told you about it. It's a piece of silicon just like what is in front of your face on your smartphones, but the difference is the data is not electric, it's optical, right? And while it goes through the chip, we can manipulate it and use it to do whatever function, which in our product, for example, is for switching. Now, the promise of photonics has been around for quite a while. It's a great platform because, one, you can do data manipulation in a much more energy efficient way because, as we call it in physics, it's a coherent process. There is no heat dissipation, so that's the power of photonics. But also, you can actually take advantage of light in terms of multiplexing and very fast movement. So you can actually send a lot more data, so higher bandwidth, and also do it with low latency, right? And these are the two holy grails when you think about computing or data processing, right? You want to do things fast, and you want to do things energy efficient. And this is what photonics can offer. And as I said, if it's made on silicon, you can actually use your CMOS fabs, you can go to your TSMCs and can make the photonic chips instead of electronic chips. So you have the power of scaling that comes with all these advantages. So when I say that it has been around for a while, then why has it not been used for all the applications? Where we see right now photonic chips being used is mostly transceivers to convert data, basically acting as an interface to the fiber world, right? And the problem is that when we start scaling the size of the photonic chip, there are losses. And this losses basically limits how many components we can stack after each other and what can our photonic chips do. So what we have built as our fundamental technology is a way to manipulate light, which is much lower loss, very small footprint, and also very fast, just like the existing silicon technology for the transceiver, right? So the way we do it is combining a new kind of semiconductor material, which is on one hand CMOS compatible and can be integrated directly in the front-end processing, but at the same time interacts with light in a much stronger way, which gives us this advantage of low-loss, large-scale programmable photonic chips. And one figure of merit that you would care about in that sense is what you see on the left side. So this is how much bandwidth or how much data you can manipulate at a time. So this is the throughput with how much power and with how much footprint, right? So this is throughput per area per power. And the comparison here, the left two are the existing silicon technologies which exist for the photonic chips, and then compared to our approach. And just as a note, the Y scale, the vertical scale here is logarithmic, so our technology is really a couple of orders of magnitude better, and this is what allows us to build these optical switches and in future much more. in terms of the market, so these optical switches are something that are really ideally suited for AI data centers. At the moment, they are mostly being deployed in the scale-out networks, so the ones that are connecting racks. But what is also exciting is that we can bring it into the rack, into the scale-up networks in the coming years. And that reflects in the market. So it's a massively growing market, right? It's a couple of billion already, but it's going to go much more. And what also comes with this adoption is the standardization. So when you use a new hardware, you need to get your software compatible to your rest of the hardware in the data center. And this is something that we are not doing alone, but it's being done by Open Compute Project in a joint group where lots of hyperscalers, existing vendors, are also working with us to get this standardization of the software layer for essentially making this hardware retrofittable to your existing data center solution. Right. Here is a short comparison of our approach versus your electronic switches, but also some legacy optical ways of doing switching, which was typically used in the telco networks. I already talked about the electronics, so I won't go into the details, right? The main advantage is the power consumption. But the other comparison here, if you look at the optical approaches, for example, by Lumentum, which is based on micromirrors, we have twofold advantages. On the practical side, our devices are much smaller form factor because they are chip-based, but also can be much more reliable because there are no moving parts, and also cheap. The second big advantage from the technical side is that it's also much faster reconfiguration possible than a moving mirror. We can go to really reconfiguration speeds of sub-microseconds towards nanoseconds, and that allows us to bring these optical switches into the scale-up networks that I mentioned. Where we stand now, so our first generation devices are ready and are being deployed with the first customers. So these are mostly different data centers, as I mentioned, for the scale-out networks. We are also looking at some other use cases, like how do you increase the resiliency of your AI network? Because you know, if there is a single device failure, you have to maybe restart your training, and that is a big cost factor for the companies that are training these networks. So this is what we are doing, and at the same time, what we are working with is to get this product into the deployment roadmap of some of the hyperscalers. So we want to really deploy it to the full extent of networking and computing that is going to happen across next few years. So this is our roadmap. So just few words. We started a few years ago, so we have done several generations of tape-out. We have built these chips with photonic fabs, including some of the tier 1 partners. What we are going to do now is to bring this 64 radix optical switch to market, get it validated for the reliability and the technical specs, and then start going into the volume production in sometime next year. We are a team of 20 people, a world-class team in terms of the expertise across photonics and semiconductor, but also now from electrical engineering, computer science, and system aspects. So what we do is not just design and build the photonic chips, but we actually build the whole rack unit boxes. And this is where also some of our partnership with Taiwanese partners come in. So we work across partners from photonic fab to system integration, and where we are also looking to engage with more partners. We have bootstrapped so far, so just a bit of financial history. So all of that was done with about $5 million US. And we have had partners not just in Taiwan, but also in German ecosystems, being in Munich, and also over in the Bay Area. So this is what allows us to engage with customers on one hand, but build the value chain needed for getting this photonics off the ground and to full deployment in future. And with that, I'm at the end. Thank you for your attention, and I'm looking forward to chatting with you at our booth. Thanks.
Thank you so much, Samarth, for your sharing on Link. Thank you. Next, let's welcome Team Straight Industries from the US. Straight Industry is a deep tech company developing the full stack of maritime autonomy, vessels autonomy, and computing, deeply rooted in the Taiwan industrial base. Let's welcome Phil Ho, the co-founder and CEO of Straight Industries.
Okay, so before we start, I want to tell you a story. The story of my relationship to Taiwan. My dad was actually born here in Taipei. And around 60 years ago, his parents decided to move to Europe, to move to France. Maybe perhaps because at the time, it was seen as a place with opportunities. But time has changed. And 3 years ago, I made the decision to move to Taiwan full-time. Because in today's world, Taiwan is the land of opportunities. So I would like to thank the amazing team at the National Science and Technology Council and the team running the Gold Card program as well for their support during my journey. Now, let's focus on Straight. So Straight, we are building the full stack of maritime autonomy here in Taiwan. So we focus on the hardware, a vessel. We focus on the software, the autonomy and the end user interface. And we also focus on the computing. So the vessel, we have designed from the keel up this vessel to be a high performance platform. It can do up to 55 knots of top speed. It can carry up to 330 kilos of payloads, and it has been designed to operate in the operational waters here around Taiwan and around this side of the world with sea states fight. And it has multi-type of applications. First, it can be used for data collection. It can be used for inspection of remote offshore energy platform, but it can also be used for government application, maritime security or harbor security as well. And we have built it here in Taiwan, in Kaohsiung. And we have moved for conceptual design to in-water testing in less than 120 days. Now the software, the autonomy. How do we turn this boat into a drone, into an autonomous platform, into a robotic platform? So we integrate different types of sensors, AIS, radar, RF communication sensors, and optical as well, to perceive the environment that is around the vessel. And we fuse that into our autonomous model in order to see what's going on around us. So then the vessel itself can make decisions on where to go, how to get there, and what to do as well, while at sea. We also designed and built our own user interface. So this is your fleet management dashboard, where you can have live visibility into your fleet of vessels in real time. On the left-hand side, you can see your different assets with the different type of payloads and mission that they are currently performing. And then if you click on any of your vessel, you can see a more detailed picture of payload, of radar, or type of communication, where it's going, and you can also assign tasks while the vessel is operating at sea in real time. And this, again, has been built here in Hsinchu with our amazing robotics and software engineering team. Now the computing, right? We turned a boat into a drone, but it's all about computing. And this is why today we're very excited to be here at Computex, at InnoVEX, to announce the launch of Helix. Helix is a high-performance processor purposely built for maritime autonomy. And it can do a couple of things. First, it sits at the heart of our decentralized computing architecture. So no single point of failure. Second, it reduces latency. When you have a platform that's moving at 55 knots at sea, computing and latency is a critical feature. And as we are moving towards deploying those assets at scale, it also offers an affordable solution there. And we are building it here with the IC ecosystem, again, in Taiwan. Every day, I'm lucky to have these two amazing leaders by my side. So first, Bilal, my co-founder and chief product officer, who's here in the room, flew over from Virginia Beach. He just retired from the US Navy. 20 years as a chief engineer on different assets within the US Navy. You can imagine the amount of expertise and experience that he's bringing to the team. And then Stanley. Stanley is our director of engineering, leading our robotics engineering and autonomous work based out of our Hsinchu office. And myself, well, I've been in the hardware tech space for a couple of years now. I already went through an IPO with a previous company doing AI IoT devices for fleet management and logistics operations. So everyone here loves to do the hard thing, roll up the sleeves and get the job done. So before I leave, I just want to say that Taiwan has made it all possible. Across shipbuilding, across leveraging the advanced industrial base to secure a resilient supply chain, but also has allowed us to hire an amazing team of engineers that are building this technology. And now, obviously, as I said, it's all about computing. So we're very excited to continue building here in Taiwan. We are hiring as well, so if you know anyone interested, please let me know. And we're excited to continue building it here. And it's all about chips and chips. Thank you.
Thank you so much, Phil, for your sharing on Straight Industries. Thank you. All right, last but not least, let's welcome Valus Computing Inc. from the US. Valus Computing is a Stanford spin-out analog semiconductor company developing ultra-low power chips for AI training. Let's welcome co-founder, Mr. Jason Poon.
All right, hello. We're Velix Computing. I'm Jason Poon, the co-founder. And at Velix, we're developing compute hardware that makes the process of training AI models faster and cheaper than anything available on the market today. The process of training versus using an AI model demand two very different types of hardware. Inference, which is the process of using a pre-built model, and that requires hardware that is pretty available today. There are a number of very capable low-power chips able to do inference. Training, on the other hand, is a totally different beast. This requires massive cloud compute. And we're talking potentially hundreds of thousands of US dollars for training a even basic model. And this puts it out of the reach of many researchers and engineers today. Velix is closing this gap. We're developing one of the first hardwares that enable AI training on device on a milliwatt power budget. And our vision is to enable anyone, anywhere, to build and own their own AI models. So we really want to democratize this space. So how do we do it? Fundamentally, the process of training a neural network is an optimization problem, trying to find the minimum of a loss function. The digital approach is really brute force. It digitizes and quantizes tons of information, it shuffles it in and out of memory, and it performs billions of gradient steps. And all of that leads to extremely high power consumption and latency. Velix is taking a fundamentally different approach. We're developing CMOS analog computing circuits that perform this optimization. These circuits are designed such that the physics of the circuit itself are solving this optimization problem. So at steady state, at the equilibrium point for these circuits, they will give you the minimum, the optimal parameters for your model. This happens naturally, in parallel, and in milliseconds. We've built hardware for a test 8-parameter setup that has demonstrated 17,000 times faster convergence compared to existing digital approaches. Our technology is patented, and we have an option for an exclusive license from Stanford, where our team developed this core technology. So how do our customers access our product? There are 3 main ways that they can do this. Velix Train is our software stack, and it makes the process of using our hardware totally seamless and compatible with the existing ML ecosystem. So today, engineers have a line of code that say, I want my model trained on this GPU. We have an equivalent line of code that says, train this on VELX hardware. And you'll get the same result, except it will be dramatically faster and require much less energy and can be done on your desk. VELX board is our single board computer we're taping out later this year and shipping to our first customers. This will be a board that our customers can have on their desk and can use to train AI models. Long term, what we're thinking about is VELX Core. These will be IP modules that we can license, and we anticipate that as our long-term revenue driver for VELX. So how do we compare with existing players in this space? You may have heard of low power technologies for training, such as the Jetson or the Coral. We're targeting orders of magnitude lower power compared to these devices. And we're one of the only solutions today that are focusing on this training problem at the milliwatt power scale and have the technology to do it. Our go-to-market focuses on edge AI. Why? For a number of reasons. First of all, the model sizes are somewhat more manageable. For instance, around 1 million parameters or less. Right? So not like a large language model with billions of parameters. We think this makes it more technically achievable for our team in the short term. Moreover, we think this is a very exciting space. We have a number of pilots and customers who are deploying very exciting edge AI solutions. We think this is a growing space, and we have the potential to make a very big impact here. So these are some listed. I'll just highlight, for instance, satellite and remote sensing. This is one application where our customers can't send data to the cloud. They're physically bandwidth limited, right? And this is an application where they need to do on-device training. And we have the technology that's going to enable this entirely new vertical. So where are we in terms of our technology and product development? As I mentioned, we've built and tested hardware that's validated our core concept. We're currently taping out our first chip later this year in collaboration with an MPW provider at TSMC. This has been funded by the United States National Science Foundation. And as I mentioned, we were spun out of Stanford, and leadership, specifically our CEO, was selected as an Activate Fellow at Lawrence Berkeley National Lab to commercialize this deep tech technology. We have a number of exciting pilots that we have lined up that are ready to test our product when it's shipping later this year. Here's our amazing team. As I mentioned, Pollock Jane is our CEO and co-founder. Deep expertise. We're both deep tech co-founders. Both have our PhDs. We have a number of amazing advisors who are helping us navigate this ecosystem. And to conclude, I just wanted to say that it is so amazing to be here in Taiwan, the capital of the semiconductor world, and as the Vice Minister mentioned, the heart of the AI ecosystem. And we really look forward to collaborating with the amazing innovators here in Taiwan to shape the future of AI hardware for the benefit of humanity. So thank you very much, and we look forward to talking more. Bye-bye.
All right, thank you, Jason, for your sharing on VELX. And ladies and gentlemen, that concludes our winning team for the 4th batch of IC Taiwan Grand Challenge this year. You may visit your booth at S0724, and please take this opportunity to interact with all these amazing winning teams. So we hope you enjoy the pitching today at IC Taiwan Grand Challenge Unveil and the whole InnoVEX 2026. We'll see you next time, and I wish you have a great day. Thank you.